Sit down. Okay, yesterday I showed you how you can make the or get the regression equation from Excel and the R square. Then we did a quick review of the equation which we derived for the shock wave, speed of the shock wave. And then we already did gone through this, we have gone through this calculation or this derivation. And then we looked at this question, okay, and I told you that when it comes to length, okay, even if it gives minus, you just put it as a test, okay, don't worry about this minus or plus, because whatever you do in the equation, you can get minus, okay. So we solved this example using these equations because it is related to the signal. And then we said that we have a Bruce Greenshield model, okay. So this is the model, and in this model we can replace k upon kj with eta, and then we go to the equation of the velocity of the shock wave, okay, and in that equation there was q value, so we replace q with q, right, meaning k into u, okay. So we have k and then we have an equation for u. So we replaced u with we replace q with k into u, and then we replace u with the equation of u. Which equation? The one which is given by Greenshield. Okay, Mr. Greenshield. Yeah, the Greenberg as well. What? You take money for this? So you do free marketing.
Was it good?
Huh?
Was it good?
You told me your car as well, right? Last time? I dragged this one. Okay. Okay, so anyways. So after putting this, the equation, the velocity of the shock wave equals to this in terms of eta. So each eta is k upon kj. And then we said that if the final density and the initial density are equal, that means eta 1 and eta 2 are equal, then velocity of the shock wave equals to this. And if you have the stopping wave, the forming wave at a red signal, then eta 2 will become 1 because the cars will stop, so k2 will be equal to kj. So eta 2 will be 1, and the equation is this one. Okay, and if you have the starting wave, which you call it the recovery wave, at the green signal, then the initial density is kj, so eta 1 will become 1, and the equation will be this one. Okay, and then we further took the value of eta from here and we replaced eta 2 with the equation of eta. Okay, so when you have the stopping wave, the starting wave, when the signal becomes green, then you can, instead of using equation with eta, you can use this equation. Okay, so this equation gives you the velocity of the shock wave, and then you only need the speeds, nothing else. Okay, you need uf and us2. Uf is what? Free flow speed, and us2 is what? Which one? Fine. Okay, so the equations become much simpler, but all these equations apply when you assume that we are following which model? The Greenshield. Okay, if you are not sure which model we are applying, we already have the general equation of the speed of the shock wave. Okay, the one from where we started this, q1 minus q2 upon k1. So that applies anywhere. Okay, but these equations are much simpler, or they have been simplified assuming that they follow Greenshield model. Okay. The volume at a section of a 2-lane highway is 1500 vehicles per hour in each direction, and the density is about 25 vehicles per mile. Then we have a dump truck which is loaded with soil adjacent to a construction site. This truck enters the traffic in one lane. This truck enters and it is moving at a speed of 10 miles per hour. Okay. So obviously it's a 2-lane highway. Each direction has only one lane. So if there's a slow truck in that lane, then if there's a slow truck in that lane,
Shockwave will stop.
Shockwave will start. Okay. So this truck is moving on this highway. So this truck is loaded and it is going upward. So that's why it's very slow. It's loaded and going upward. So it becomes very slow. And the distance it travels on this highway is 2.5 miles. So these people have to suffer because of the truck for how much distance? For 2.5 miles. Okay. Now the flow of 1500 vehicles per hour is very high for one lane. If it is a 2-3 lane highway, it's not a problem. But for one lane, 1500 vehicles per hour is very high. Okay. So if you have a slow vehicle in front of you, then normally you would try to pass him from the other lane, right? But the other lane is also full, so there is no chance for you. You have to follow. Okay. So with this restriction, now you will follow behind the truck. If following behind the truck, that means your speed will be okay. So this is the speed of the vehicles now, and so behind the truck they form a platoon, a queue. Okay, they are not calling it a queue. Okay, and the reason is that they are not stopping. Okay, the reason is they are not stopping. Queue is what? That they will stop somewhere and then they will move, then stop, something like this. Okay, so they call it a platoon because they don't stop at all. There's no stopping here. Okay, but it means the same thing. The concept is the same. The people who are affected by the truck. Okay, they don't want to call it a queue because they are not stopping. Okay, so the platoon has a density of 100 vehicles per mile and a flow of 1000 vehicles per hour. Okay, how much was it? 1500. Density 25. With the truck, it became density 100. Okay, because now they are going very close to each other. They are going slow and very close. Okay, the same thing which happened at the signal. Okay, and so the flow is now less because they are slower, so the flow is less. So we have to find out how many vehicles will be affected by that truck, or how many vehicles will be in the platoon. Who are the people in the platoon? The people who are affected by the truck, the people who are behind the truck. Okay, so how many vehicles will be affected by the truck when the truck leaves? Got it? Clear? Okay, so what are the things which are given? Initial flow, initial density. Final flow, final density. The speed, which speed is this?
Truck speed.
Truck speed. So it will become what now?
Shockwave
speed.
No, it's not the shockwave. It's the final speed of the vehicles. Final speed of the vehicles, and this is the length for which truck is traveling on this highway. Okay, the distance in which the truck is affecting, or the distance up to which the truck will be on the highway. Clear? The data is clear. Okay. Okay. These are the steps we follow. Okay. First of all, we will find out the speed of the shockwave. Okay. Speed of the shockwave. We know they did not mention we are following Greenberg model or any model. Okay. So we don't have to use any model here. Speed of the shockwave equals Q1 minus Q2 divided by K1 minus. Okay, Q1 initial flow 1500, final flow 1000, initial density 25, final density 100. All these values are given. How much is it?
Minus 6.7.
Should we write the minus?
Huh? Just for fun. Okay. Relative speed of the platoon. Okay. We did one derivation earlier where we were using relative speed. In fact, this equation, when we were driving this equation, we used relative speed. Relative speed means what? I call it UR. So you will tell me what is UR. What was relative speed? What was the difference? Difference between what?
The final speed
And
and the speed of the vehicle now.
final speed of what then?
Like when they reach the track, like in the platoon. After the shockwave.
After the shock. This is the shock wave, right? So yeah, it's a difference between two values, yes. And we are talking about relative speed. So difference between speeds, right? Which speeds now? Tell me.
Initial speed and shockwave speed.
Initial and shock wave? It was initial and shock wave? No. Actually, it can be, you can have relative speed with initial, you can have relative speed final as well. Depending upon which speed, from which speed you are taking the difference. So if I take the difference between shock wave speed and final speed, it will be relative speed of the after. If I take the difference between shock wave speed and initial speed, it will be the relative speed before. Okay, so it can be both. You can have relative speed before and after, both. Okay, but in this case, what are they asking for? Relative speed of what?
Platoon.
Platoon. Okay, I'm interested in the platoon, right? What? So when the platoon happened when?
After
The truck. After the truck. So when the truck entered, the speed of the cars became what?
this.
10, right? It became to the speed of the truck 10 miles per hour. Okay, let me just check. Are we doing what minus what? So it's speed minus the shock wave speed. Okay, so it will be 10 minus how much is that? So it was a speed minus the shock wave speed.
16.7.
Before shock.
Behind the truck. Behind the truck, yes. They are following the truck. After truck, I mean following the truck. Okay? Clear? Okay. So now then we need how much time the truck is spending on this highway. How do I calculate the time?
Speed and distance.
Yeah, they told me the speed of the truck, and they told me that the truck will drive on this highway for 2.5 miles. Okay, so there is no conversion required here. Tell me the time. Four?
4 to 4 minutes. 4 hours. I see.
No, sorry, it will be the other way around, right? Other way around. How much is it?
0.25.
Huh?
0.25.
0.25? Now this is in hours, okay?
15
So
minutes.
15 minutes.
15 minutes.
Okay, so truck is on the highway for 15 minutes. Okay, so how much is the length of the platoon? Length meaning how much distance the platoon will cover. How do we know that?
Speed by time.
Yeah, which is speed?
Relative speed.
Relative speed. Okay, so I'll use relative speed. Okay, so I know the relative speed of the platoon. Relative speed of the platoon. So platoon is growing by the speed of this much. Okay, and it will keep on happening for these many hours. So what is the distance here? Speed is distance upon time, so distance equals what? Now this is what?
Mile.
Nice. Clear? Clear? Any problem? Okay. Then I have to find out how many vehicles were in the platoon. Okay, so platoon is how long? 4.18 miles. In 4.18 miles, how many vehicles I have?
From the density.
How do I know? Density. Okay, density is vehicles per mile. I know that platoon has a density of 100. Okay, platoon has a density of 100 vehicles per mile. So in 4.81 miles, how many vehicles will I have? How many?
480.
418. Okay, so we were required to find out this basically. How many vehicles? I can use n here. Oh, fine. We are not using it. Okay, so we are required to find out how many vehicles are in the platoon or in the queue or whatever you want to call it. Okay, so they gave me density. Okay, I know if I multiply density by distance, I will get number of vehicles. Okay. So my problem was how much is the distance. Okay. For distance, I need time and speed. For distance, I need time and speed. Time, I can find out from the truck because I know the speed of the truck and I know how much distance the truck covered on the highway. So speed was 10 and the distance covered by the truck was 2.5. So I know the time. Okay, now my main problem was the speed. Okay, I need, because I am talking about the platoon, so I need the speed of the platoon. Okay, I have the speed of the vehicles. I have the speed of the vehicles, and I have the speed of or I can calculate the speed of the shock wave. Okay, so speed of the platoon will be the relative speed between them. The speed of the platoon is a relative speed between them. What does it mean? The shock wave, now you can see the shock wave is minus, right? So it's going backward. This is what we said, right? It's going backward. So because of the truck, the number of, the vehicles, every hour 6.7 miles of the length is getting affected by the shock wave behind. Okay, so there is an entry point of the truck, right? When the truck entered at, let's say, point A. So behind point A, the shock wave is created at a rate of how much? 6.7 miles per hour. So the truck continues for 1 hour. Behind point A, I will have a platoon up to 6.7 miles. Got it? Got it? Behind point A. But is the truck staying at point A? Is the truck staying at point A? Or is it moving? Moving, right? So the effect of the truck is going backwards, but those vehicles which were behind point A, now they are also moving forward, right? So we have a platoon before, and the forward part of the platoon is moving ahead of point A. Okay, so there is a platoon created before, and the platoon which was already there is moving forward. Okay, so the total length is increasing backward and forward both. The shock wave is having an effect behind point A as well as in front of point A. In front of point A are these people who are behind point A, now they are moving forward. Got it? Okay, so if you add both these effects, then you have the relative speed 16.7 miles per hour. This is overall now. This is the overall effect. So the truck stays on this highway for 1 hour. The whole platoon will be how many miles? 16.7 miles. And what was this? 6.7 miles? Yeah, behind point A, behind the starting point. Got it? Okay, so this is just the effect of the shock wave behind the starting point, and this is the total effect. This is the total effect, because shock wave is moving, right? That's why they are calling it platoon, they are not calling it Q. Okay, so you find out the total effect of the shock wave, the total speed of the shock wave, behind and forward both. We call it the relative speed. Then you find time, you multiply, you divide distance by speed, you get the time. Then you multiply the speed with time, you get the distance of the shock wave. Okay, and then you multiply distance with density, you will get number of vehicles in the shock wave. Clear? Okay. The main point here was to find out the total effect of the shock wave. Total effect is what? The relative speed. Got it? Okay. Any questions? Any questions? Clear? Ibrahim? Okay. Your face and say okay. Okay. He did senior with me, that's why he's saying this, right? Okay. Now, we did one example yesterday, I think. This one, right? Yes. Now, in this example or the derivation we did here, do you see any relative speed here? No, there's no relative speed. We did this derivation and we were using relative speed, right? Okay, why didn't we use relative speed there? Why are we using it here? And why are we using it in the example today? Okay, the difference is what? I told you. In the previous example, the example which we did today, we were calling it what? Platoon. And when we are doing it here, we are calling it what? A Q. Okay. Now when the signal becomes red, what's the speed? 0. So if you take the relative speed, it will be what?
0.
Something minus 0 or 0 minus something, right? So in the end you will get what? Speed of the shock wave, right? Got it? Okay. So if you are taking relative speed on a red signal or a green signal, okay, then one of the speeds is
0.
0. Okay. So your relative speed becomes equal to what? Speed of the shock wave. Got it? Okay. Clear? So whenever we need the total speed or total effect of the shock wave, we should take relative speed. But when it comes to a signal, the other speed is 0. So the relative becomes equal to shock wave. Clear? Clear? Okay. So we have again a 2-lane highway. We are not making more than 2 lanes. We don't believe ourselves. 2 is enough. Okay. And there's an accident. Okay. Density before the accident is given, and the accident blocked 1 lane of the highway, and it remains blocked for 20 minutes. Okay. This incident creates obviously a queue behind the accident site. Okay. So if the flow on this highway can be described by Greenshield model. okay, then how many vehicles will be affected by the occurrence of the accident. So now they are saying don't use the general equations, use the equations which we derive with the Greenshield model. Okay, so for this flow or for this highway, they have given me the mean free speed, the free flow speed, and they have given me the jam density. Okay, so what do I know? I know the initial density, I know the jam density, I know the mean free speed. Okay, clear? Now, for the Greenshield model or the equations which we have with the Greenshield model, they need eta 1 and eta 2. Eta 1 is the initial and eta 2 was the final. And eta means what? Eta was k over kj. Okay. Just assume n is eta. Okay. Okay. Looks like eta, right? Close enough. Okay. Near the exams, I will be having questions. Why is this n when it was eta? This is eta. Okay. Eat it. Okay. So eta 1 I can find, right? How much is eta 1? The initial density upon the jam density. So 40 upon, how much is it? 100. So 0.4. Eta 1, no problem. Eta 2, how much is eta 2? Now, vehicles are stopping. How much is eta 2? It's 1. Okay, and vehicles will stop, they will stop close behind each other. Okay, so the density will be equal to jam density. Okay, so it will be eta 1. What happened? Okay, for such cases, so it's the stopping wave. They were moving and they stopped. Not because of red, but because for any reason, but it's stopping. Okay, so the phenomena is the same. Okay, it's the same phenomena. So for this phenomena, we have UF into eta 1. Okay, the speed of the shock wave equals the free flow speed into eta 1. So free flow speed is how much? 60. Yes.
It's 24. You wrote 14 here.
Where?
You wrote 14.
It's 60, huh?
Yeah.
So 24 miles per hour. Okay, so what are they asking for? Determine how many vehicles are affected by the occurrence of the accident. Okay, so I to find out the number of vehicles, okay, like we did before, we need length, we don't have the length, right? We need length, we need speed, and we need the density. Okay, length is not given, but I know the time. Okay, the incident is taking 20 minutes. So the road will be blocked for 20 minutes. Okay, so in 20 minutes, the shock wave is going at a speed of how much?
24.
24. Should I calculate relative speed? I did relative speed in the last question, right? I calculate relative speed. Should I do it here?
No.
It's the same as the shock.
Yeah, because relative speed is speed minus shock wave speed. Okay, the speed of the flow is what?
0.
So number of, sorry, I need to calculate the length. So how do I calculate the length? The speed is this much and the time is this much. Give me the distance. 8 what? Miles? Did you do the conversion? 20 minutes? 1 hour? 1 hour 3? You forgot your mind?
8 mile.
8 miles?
Hector, I told you, half an hour ago.
I don't trust you. Okay, so the number of vehicles, now we know the length, we know the density, and we know the, we know the length.
Yes, by density.
No, first of all, I need to get the what? Oh, yeah, I already did.
You already calculated.
Yeah,
So
so
800.
density into the distance, right?
Yeah.
How much is it?
800.
Density is 100, so 800 vehicles. Okay. So there was a stopping wave because of something, the lane blocked. Okay, it remained blocked for 20 minutes. Okay, and they are saying the flow follows the Greenshield model. If it follows the Greenshield model and the wave is stopping, then I know when that the speed of the shock wave can be equal to this. Okay, if this is the speed and the shock wave will remain for 20 minutes, then how much distance it will affect. So the speed you have and time you have to calculate the distance. Using the distance and the density, then you calculate how many vehicles it will affect. Clear? Okay. Okay. Studies have shown that the traffic flow on a single lane approach to a signalized intersection is following Greenshield model. Jam density is given. We have to find out the velocity of the stopping wave when the approach signal changes to red if the density on the approach is 45 and the space mean speed is 40. Okay, and at the end of the red interval, what length of the approach upstream from the stop line will be so length. Okay, if the red is for 35 seconds. Okay, so first of all, we have to find out the velocity of the shock wave. Okay, when the signal becomes red, what is the velocity of the shock wave? And if the signal remains red for 35 seconds, then how many vehicles, not the vehicles, what is the length of the vehicles that will be in the, or what is the length of the road that will be under the shock wave? And they have given me the jam density, they have given me the space mean speed, and they have given me the density before the red. Okay, clear? So again, it's a stopping wave, right?
Yes.
It's a stopping wave. Okay, so I can calculate the speed of the shock wave like I did here. Okay, what was this? What was this?
Free flow speed.
Free flow speed. Do we have the free flow speed?
We have the speed before the.
But we don't have the free flow speed, right?
Yes.
Okay, so I will use the assumption which is given that it follows the Greenshield model to calculate the free flow speed. Okay. According to Greenshield model, speed equals free flow speed 1 minus k upon kj. Okay. Now I have the space mean speed before. Okay, which is 40. So u is 40. I am trying to find out what? UF, right? Okay, and the density before is 45 and the jam density is 130. Okay, so UF 1 minus 45 divided by 130. Okay, so how much is UF? Hmm? 61.2. Okay, so I have the free flow speed now. I can find out the speed of the shock wave, which was what? Eta 1 into the free flow speed. So free flow speed is 61.2. Eta 1 means K1 upon Kj. Okay, eta 1 is K1 upon Kj. So this is my K1, initial density, and upon the jam density. So 45 upon 130. How much is that? 0.35 miles per hour. Clear? No? Okay.
Oh no.
No?
This was
21.2.
It's a 1.
21.2.
21.
Yeah.
Okay, I think the equation has a minus sign there. I believe so. Okay, speed of the shock wave. We did the this part. Okay, velocity of the shock wave. Okay, now I need the length which is affected by the shock wave. It's easier here because
We have time.
we have the time and you already have the speed. Okay, so distance equals to what? How much? You have the speed of the shock wave, and the time for the lead signal. And again, you have to do the conversion. Tell me. Now what is this? Miles? Miles?
Yes, 0.2 miles.
0.2 miles. Okay, any problem?
So in Shockwaves speed, use any which equation?
You can use this one if it says follows the Greenshield model. Okay, and then we have the general equation which is Q1 minus Q2 upon K1 minus K2. That is applicable everywhere. Okay, so if there's, because this one is easier. You see, you need less things. Okay, so if the assumption is given, then I can use this one. If the assumption is not given, then we have the general equation. We will use it anywhere. Clear? Clear? Any other question? Okay, Greenberg model. Okay. First of all, what was the Greenberg model? Is given here. Sorry. Okay. This is the Greenberg model. Okay. This is the Greenberg model. So it has ln, the natural log in it. Okay. This was the constant. What was this one? Anybody remembers? What was this 90? What does this indicate? 90. It's a constant, yes. Which one? Jam density. Okay. So jam density, and this was C. Okay, some sort of speed. Okay, but it's a constant, 45. Okay. So we have a traffic signal near the school, going back to the town, and during the green phase for school kids, so vehicles must stop. Green phase for the kids. Okay. So when they will stop, when the kids will go, there will be a queue. The kids take 40 seconds. Okay. If they are my daughters, they take more. Okay. And they can go anywhere. Like I need 40 seconds to just make sure they are behind me. Okay. Traffic flow can be described by this model, and the model is given with the constants which you require. Determine the number of vehicles that exist in the queue during this phase. Okay, so at the end of the phase, how many vehicles will be in the queue? Assume space mean speed of the traffic within the school zone is 20 miles per hour. Okay, so now it is following Greenberg model. So I cannot use that equation, UF and eta 1, I cannot do this here. Okay, that is with the Greenshield model. Okay, so I don't have any simplified equation for the Greenberg model. For the Greenshield model, we derived new equations for UW, right? And then we said if this is the case, UW equals to this, this is the case, UW equals to this. Those equations will not work. Okay, so I have to use the basic equation of UW. What was the equation of UW? What is the basic equation of velocity of the shock wave? Yes. So Q. This is the basic equation. Okay, what do I need here? Tell me. What is missing? What do I have? They just gave me the speed in the school zone. Which speed is this?
Space means speed.
Space mean speed. Okay, this is the space mean speed. Okay, which one is this, before or after? Before, right? It's before the shock wave.
Yes.
Shock wave is the signal, right? So when we have a signal, okay,
So the final
which of these values do I need? Q1, I should have a value of Q1, right? There should be a value of Q1. Initial flow, there should be a, okay, Q2,
0.
0, okay. K1, there should be a value, okay, is it given?
No.
No. Can I find out? Is there any equation given which can give me the value of K1? The model, right? Because we have the speed. The model needs what? Speed. So if you put the initial speed, you will get the initial density. How much is that? So U1 is 20, and this should be equal to 45 into log of 90 divided by K. So I need K. How much? 0.7? 57.7. Okay, and what about K2? The final density. Final density, yes, yes. 90. Okay, final density is the jam density. Okay, final density is the jam density. Okay, and if you are familiar with the Greenberg model, so jam density is a numerator with the log. Okay, so whenever the Greenberg model is given with the constants, this constant is my jam density. So 90 is my jam density. Okay, so K2 is 90. Okay, so what is the speed of the shock wave now? Can I find out the speed of the shock wave now?
Yes.
Oh,
We need Q1.
Q1, yeah. So what do I do? Q
We
equals?
have speed and we have.
Q equals Q. UK, huh? What? Q equals Q. Okay. So I need K1 and U1. Do I have both? K1, U1, both? Okay. So K1, U1 is 20, K1 is this one. So Q1 is how much? How much is it? 55?
154.
115.
Okay, so now you can give me the speed of the shock wave. Q1, what we found, Q2 is 0 because the signal is red. K1 we found, okay, this one is K1, and K2 is the jam density, which is 90 from the model. So how much is the speed of the shock wave?
35.7.
Okay, what we are asking for, what they are asking for, determine the number of vehicles that exist in the queue during this phase. So now you know the speed of the shock wave. Okay, and I need the number of vehicles in the shock wave. Okay, so to get the number, I should know what? The length of the shock wave. Okay, so you know the speed and you know the time, right? Time is how much?
20 seconds.
20 seconds, 40 seconds.
40 seconds.
Time is 40 seconds. So the speed, the shock wave will go at a speed of 35.7 and it will continue for 40 seconds. So how long will it be? 90 what? K2? 90? Ah, K2 is 90, yes.
So speed of shockwaves have
0.4.
Has what?
you get it. One.
Yes, sir.
So we get basically because
You got
Q1
what?
Q1 we have
Yes.
Q2 0. K1 we have
K1 is 57 and K2 is 90, right? 57.
0.4.
0.14 is what now? 0.4 is what now? Miles? Okay, and you did the conversion for time, right? Okay, so now you have the distance and now you also know the density. Density is 90. Okay, K2. So how long is the shock wave?
36. No, vehicle.
Length,
Number of
length.
vehicle.
Number of vehicles? Ah, yes, number of vehicles. 36 vehicles. Okay. We calculate the speed. For the speed, we needed some parameters, okay, like the initial density and the initial flow. We didn't have that. So for initial density, I use the Greenberg model. For the initial flow, I use a basic equation, which is Q equals Q. Okay. So I completed the parameters. Then I found the speed of the shock wave. If shock wave speed is this much, then how much length it will take, speed and time. And then if this is the length it has taken, then how many vehicles will be in this length? So I have the density and I have the distance. Clear? Sure. Okay. Any questions?
Greenberg model. It's a standard that we multiply 90 by the line.
What?
Like to calculate the number of vehicles, standard only 90 multiplied by D.
No.
Because the jam density always 90.
No, jam density is not always 90. Jam density is whatever the number we have here. So this number can change. But the model shape is this. Constant multiplied by log of a constant upon something.